When they invited me to come and talk to faculty, I said I also want to talk to students because, as you would see, hopefully, when you want to bring about some change, you want to bring the latest science of learning into university, teaching and learning, convincing faculty is not enough. You've got to convince students as well. Because what got you here is not necessarily going to make you great going forward. And that's where the science comes in. Right? So I want to share some of my experiences, both as a teacher and also as a researcher in the learning sciences. How many of you have heard what have you heard learning sciences? What does that mean? One hand up. Anybody else who knows what learning sciences is? So you've basically come to a talk not knowing what the learning sciences are. That's brilliant. That's good. Okay. So yeah, that shows that you want to learn about new things that you know nothing about. Okay, that's good. So very quickly, learning sciences is basically the science of human cognition and human learning. It's basically trying to understand how does the mind and the body now, how does the mind and the body, how do we learn new things? Well, how do we process new information? How do you integrate new information? How do you encode it? How do you retrieve it? How do you transfer it? How do you apply it? And so on and so forth. So there's a whole body of research on that. And we've been trying to do that for, I would say, a good 70, 80 years after World War II. Okay? And a lot of work has gone in, and I'm going to give you an overarching view of what that research has said, and maybe start to provoke you a little bit in what you think is good learning, or what you think good learning looks like, or good teaching looks like when you see it. All right? So I'm going to start with this, because it's the third slide, so it's good. We just start with the third slide. As the title said, this is research 4 decades ago almost. You can see from the title. Here, researchers went into classrooms, university classrooms. They picked known good lecturers. Okay? They went into the classrooms, they studied what lecturers did, and they found, yeah, these are pretty good lecturers. They structure it well, they explain it well, and if you had a checklist of what good teaching is, all the checks off. They also asked students, did you learn something? Was this lecture good? Did you learn something? Did you understand it? Check, check, check. Right? They had peer faculty come in and observe the lectures. Check, check, check. So everything was good. Very good courses, very good lectures. Except when they probed understanding of students about the concepts that they'd learned. Students could do everything that was taught, right? But if you change the problem slightly, or you introduce a new novel context, it's as if they did not know anything, right? And hence the title of this course, When Good Teaching Leads to Bad Results. So as a scientist, a science of learning, as a scientist, you need to articulate what the problem is. Why is it? I mean, it's fairly intuitive, right? I grew up listening to lectures and learning from it. You probably spend 95% of your time doing that as well. Why is it that you have disasters of well-taught courses? The problem is not that we learn poorly from bad lectures. So I've told my faculty early this morning, please do not give bad lectures. Okay, so I hope they don't give you bad lectures. The problem is that we learn poorly from very good ones. And there's nothing you can do about it. Because that's just how the cognitive architecture is. And that's the problem that we're trying to solve. And from a student standpoint, if you go straight into a telling, it's very intuitive. Look, I don't know something, can you please just teach me? It's the most intuitive thing to ask for. Why aren't you telling me what it is? Why aren't you explaining me what it is? It seems very intuitive, but it's not the most optimal. It doesn't mean you won't learn anything. It just means it's not the most optimal way of learning. You could do a lot better. So why is it that we learn poorly even from very good lectures? Let's understand that. First is the problem of seeing. Right? So a thought experiment I normally give is, imagine you're watching a movie. Right? It's a very entertaining, very engaging movie. Imagine the person sitting next to you is an acclaimed director, somebody who's an expert at making movies. You come out of the cinema, I ask you a question. Did you watch the same movie as the director? Yeah. The person who's sitting next to you watched the same movie. But if I asked you, did you see what the director saw? Why not? It was the same movie. It was right in front of you. It was not like a particular part was open to the director and the other part was open to you. It was the same perceptual stimulus, right? Yet, the director would see very different things from novices, from you, or even from me. I'm not an expert director, so it doesn't matter, right? The director would see things that are right in front of you that you don't see. For example, the deep structure, the critical features, the angles and the perspectives that are completely oblivious to you. It's right in front of you, but it is not. And that's the fundamental thing about cognition, of seeing. That seeing is not simply a perceptual exercise. Learning would be so easy if it were just a perceptual exercise. I can see it and therefore I encode it. No. Seeing is a cognitive exercise. You see with the knowledge. You see with what you know, right? And that's why learning is so hard initially. Because to deeply understand something, you need to know what to see, what to look at, the deep structure. But because you're a novice, you are missing precisely that knowledge to see that deep structure. So you're kind of, in a bit of a problem. And your teachers are also a bit of a problem. They're experts. They look at their lectures, and if they've done a good job, well, this is so clearly explained. It's clear, it's right in front of you. I see all the things that are important in my lecture. And they make an assumption just because they've shared it, they've delivered that lecture, that you see it too. And you think you're seeing it, but you're actually not, because you don't have the knowledge to see it. You get the idea? And it doesn't matter whether you're watching a movie, or you're looking at a proof in mathematics, or a piece of art, or engineering diagrams, or an essay. It does not matter. Any domain stimulus, experts see very different things from novices. And they see things differently as well. And that's one of the reasons why if you go straight into a lecture, straight into asking for an explanation, it seems intuitive, but it's not the most optimal. Because it just gives you an illusion that you're seeing things when in fact you're not. So the first job of teaching, and I tell lecturers this, faculty this, is actually not to teach. The first job of teaching is to prepare your student to see, and then show them. So expert knowledge is important, but preparing the student to bringing them into a state where they can actually see what the lecturer is trying to show is even more important. And the message to students is that if you're about to learn something new, if you go straight into telling or into watching something or straight in, careful, straight into something, asking straight for a lecture, it's also not optimal for you. The question for you as a student, as a receiver, is how can I prepare to see what the lecturer is trying to show me? Okay? That's the problem. So if you can solve this problem, many of the problems of learning are going to go away. But unfortunately, this is not the only problem. Right? Then is a problem of understanding. How do you understand new things? And this is the idea that even if you can see something, it doesn't mean it's integrated with your networks. Okay, let me do a memory experiment just to illustrate what goes into integrating new information, right? Because researchers have studied memory. How do you remember things? Because to remember things, you need to be able to encode things, right? And encode things connected to what you already know. All right, so I'm going to give you a memory test. Ready? I'm going to give you 9 statements about who did what. So somebody did something, and you're going to have to remember all 9 of them. Okay? And I'm going to give you just enough time. So it's time pressure test. Tests are something you're very used to, right? This is another test, except it doesn't matter. Go. Okay. Right? Now you can try to recall who did what, okay? Yeah, I'll give you some time, yeah? You can recall, right? Is there anybody who got full 9? Anybody with the 7 maybe? 5? Okay, maybe it's the time of that evening on a Monday. So basically, if you do this experiment, the average results are around 4 to 5, right? Another thing is you are more likely to remember the first 2 and the last 2 more than the others. And you're also more likely to remember something that connects with you. So if you're a movie buff, you'll remember the person who made the movie. If you're a sports buff, you'll remember the sports person, and so on and so forth, right? So this is fairly standard. But 4 or 5 is not what we want from students, right? We want, what do you want? 9 out of 9? What? Sorry, do you want 9 out of 9 or not? Clearly, you didn't do very well on the first test, right? So now let's try to give you 9 out of 9. Suppose I could give you 9 other statements, and I guarantee you, with just a minor tweak, you'll get all 9 correctly and effortlessly. It's like your memory has suddenly doubled in capacity. Would you believe that? No, it's not magic. But I will make you remember even if you don't want to. Just by doing one small trick. Ready? Ready to remember 9 more statements? Yes. You guys are not an enthusiastic bunch. Okay, here are your 9 statements again. And this time you will remember them effortlessly. Okay? Right. Who set sail?
Columbus.
Oh, there you go. Who sang a song? Elton John, right? Who wrote the play? Wow, you guys are memory geniuses. It's like I'm not even asking in the same order of things, right? What happened? What happened? How could you remember suddenly when earlier it was computationally, from a processing standpoint, it's the same amount of information that you're processing, right? I did not increase the information, I did not decrease the information. It's exactly the same amount of information. But suddenly you're remembering things. And that is the idea that what I did was I activated your prior knowledge, right? I simply made certain assumptions that, okay, this is a crowd that should know about these things. And I just activated those. And with the same amount of information, you went from average to superstars, right? In memory. And that's what happens when you want to understand something. How do you go from average to superstar in understanding? And the idea there is, can you connect new knowledge, new information with your priors in a way that it connects? When you can activate your priors, it helps you. Did you realize that how easy it was to remember? So it's not that you were remembering more, it was effortless. Yeah, okay, you didn't have to look twice. You didn't have to have any device for, invent any procedures to remember those things. No, it was just effortless. Right? So what activation does, it makes your processing of new information easier, which means you can integrate the new information into what you know much easier. And that's where deep understanding comes. Okay? What happens in a lecture, when you go straight into a lecture, is you're trying to do all of that. And that's why processing is difficult, because you're not activated properly. And if you're not activated properly, I don't mean physically, and you're sleeping after a night out. No, not that. Just your cognitive system is not activated properly in a relevant way, and therefore you're not integrating information. I've just shared with you a couple of problems, right? A couple of problems on learning, why we learn poorly from straight lectures. Just focus on the problem of seeing. Don't go into straight lectures, because you won't be able to see what experts are seeing in them, much as you may want to. B, it's not connecting with your prior knowledge in ways that you'd want to, and therefore you will not integrate that new knowledge into deep understanding. Right? So how do we solve these 2 problems of seeing and understanding, or connecting with prior knowledge? Okay? Let's look at science. All right. The first is the idea of scaffolding. Right? This is more than 100-year-old idea. Comes from Soviet psychology back in 1910s, around the First World War. Vygotsky. Have you heard of Vygotsky? Now you have. Okay, Vygotsky had this brilliant idea that if you want to learn or you want to grow, you cannot just do things that you can do without any help. So that's the green circle. There are lots of things you can do without any help, I hope. Right? If you keep doing the things you already know and you're good at, you don't need any help with those things, you're not going to grow. You're just going to be where you are. You also cannot do things that no matter how much help you get, you're not able to do. Maybe run like Usain Bolt. Or in my case, do salsa. I have 2 right feet. No matter what amount of help would help me do salsa. Okay? Where you want to be if you want to learn and grow is in the middle zone. Where you can't do it right now, but if I give you some help, you should be able to do it. You should slowly be able to pick it up. You can't swim right now, but I throw you into a pool, provide you with the necessary support and then you're able to swim. You can't do calculus right now, but right? That's the idea. So that's the zone where you want to be. Now, what is the nature of this zone? How do I know or how do you know that you've entered this zone? Suppose your teacher, or suppose I give you a task, and you're able to do it successfully, without any help. Have you entered the zone? No, you're still in the green zone. Okay, then I increase the task, I make it harder, and you're still able to do it. Are you in the zone? Still not. When do you get into the zone? Does success give you information that you are in the zone? No, it's failure. It's when I give you a task that is sufficiently beyond your current skill sets and knowledge, when you actually fail to perform that task successfully, it is the failure that gives you information that I have now entered the zone where I can learn and grow. Of course, many students think that once they've entered that zone, they say, oh, this is hard, I struggle with it, I'm failing, I can't understand this. This is not for me. That's the wrong conclusion to make. You should be celebrating that you're now in the zone where you're finding it a little bit challenging, a little bit struggling, you're failing, maybe flailing, but that's exactly the right zone to be in, provided there is support and guidance available in that zone. So the first thing that we learn from the science about what it means to learn and grow is you got to get inside the orange zone. And the only way you will get inside is to try to do things that are beyond your current capabilities and skill sets. Or ask your teachers to give you things that are beyond your current skill sets and knowledge. Because that's when you're getting into the learning zone, right? That's one. Failure is the information that drives it. The second thing is, once you're in that zone, how much help should you get? You clearly can't do this by yourself. Should I give you all the help that's necessary? Or should I just give you a little bit at a time? Just to see how you use it. How do students feel about it? Do you want all the help you need, or do you want a little bit at the time? Are you like the student who says, no, don't give me help first, I want to try it. And then the person says, okay, let me explain to you. No, wait. Okay, just give me a hint, please, just a hint, a tiny hint. Or you say, okay, show me the explanation. I couldn't do it. Obviously, you show me the whole thing. Which one are you? Second one? First one? Just give me a little bit. You're like the feeblest of hints guy. Just give me a nudge. I leave it to you to answer your question. You look at yourself in the mirror tonight and answer that question honestly, all right? Who you are, right? And different situations, we are different people, no doubt. My point is, what will give you the biggest growth is if you take the least amount of help. If that doesn't work, if that still leads to failure, then you ask for a little bit more. And then a little bit more. but never the full guidance. Okay? Because if you take full guidance, the cognitive effort is in the structure that's provided you. You have not done the work. Learning is for the person who actually invests the effort. If an expert or a facilitator or a guide takes on the load, the more load they take on, the less you learn. Or if a tool, when we talk about AI, you're learning how to write, and you use AI to help you how to write, you're never going to learn how to write. You might be able to produce good work, but you have not learned how to write. That's the point. So be very careful when you're learning new things. A, you need to enter into this zone, and B, when you're in this zone, resist help or keep it at an arm's length and only take it when you absolutely need it, because that way you're making sure that the effort is put by you and not the tool or the expert or somebody else. And that is if you're learning something new. Now, it's a different matter when you already know, when you've already come into the green zone. You've learned it, and you've learned it to a level where you can do it independently. So you went into the orange zone, you learned it well, and now you don't need help, so you're back in the green zone. There you can use tools all you want, because you already know how to write, you already know how to do calculus, you already know how to write a poem. Then you can get help from tools, and you can improve your productivity with tools. So be very mindful. Where are you? Are you in the learning zone, or are you in the performance, productivity zone? Okay? All right. So those are the two features, right? As I said, you need the failure information, you need minimal guidance, keep the effort on yourself. And it's not easy, but that's how learning happens. No. You know, when you learn a new sport or a skill, it's obvious that you will suffer a little bit. Nobody questions that. But for some reason, you know, academia, like if you learn math, science, we expect that, no, it should be easy. I should be told. It just doesn't work as simply as that. So that's from 100 years ago. From about 50 years ago, people have started studying children, because, you know, our learning curves are the steepest when we are very young. You know, the first 7 to 10 years of our lives are steep learning curves. And the idea is that if you can study what happens and how do we learn so well in these early years, then maybe we can bootstrap that somehow. There are some capabilities. So this effect is called the play effect, where psychologists have gone in and studied young children playing with toys. Okay, toys. So I did the same experiment earlier, and I'll do it with you. So I'm going to divide you into two groups. Group 1, okay? Group 1, Group 2. Okay, so I go to Group 1. Imagine you're 3 to 5 year olds who love to play with toys. And I say, hey kids, here's a new toy. Pretend, okay? Pretend. Here's a new toy. Would you like to play with it? Yes. Okay. Like faculty and student alike, huh? In the morning, you're just like your teachers, huh? Or as enthusiastic. Okay, and I say, okay, fine, you want to play with it? Play as you like. And I let you play, and I observe how you play. Play as you like, right? And then I go to Group 2. And I say, hey kids, here's a new toy. You've never seen it. You've never played with it. Would you like to play with it? Yes. My God, these are not, you haven't learned anything from them, huh? At least pretend, okay? Do you like to play with it? Yeah. Oh, thank you. All right. I said, but wait, you have not seen this toy, you've never played with it. Let me first show you how to play with it. Watch and learn. And I show you, this is how you play with the toy. If you press this button, this happens. This button, that happens, and so on and so forth. And I teach you exactly how to play with the toy, how the toy works. And I said, now you play with it. And play as you like. And I observe both groups. Who do you think spends more time with the toy? Who do you think invents more strategies to figure out how the toy works? Who do you think is more creative in using the toy and playing with the toy? It's up to 3 times as creative. Now think of knowledge, ideas, not as these physical toys, but as conceptual toys. And a big part of understanding and creativity comes with playing with knowledge, playing with ideas. Right? And that's exactly what happens. Now think about how you're taught most of the time. Group 1 or Group 2? I'll leave you to answer that question in the mirror again tonight. Yeah? But what this research says is that there is something about playing and tinkering with knowledge, ideas, physical objects before you learn something new. Okay? There's something about it that if you can utilize, then you can learn really deeply. There are effects on understanding, there are effects on creativity, and so on and so forth. Right? And this is how children's learning curves are, very steep. Okay? This is the play effect. Then there's a thing called generation effect. And as students, you like to have your notes, you have everything specified for you, it's very clear what you need to study, read, memorize, understand. It should be very clear. You should be given and you're confident. The reason why, part of the reason you've made it to university is obviously you're smart, you can take some material and really read and understand it. You like to be given the information. So this is generation effect. Okay? It's a simple memory experiment. Again, Group 1 and Group 2. Group 1, Group 2. I'm going to ask you to remember word pairs. So for example, I'm going to give you a stem. In this case, it's rapid. And you have to guess a word that's associated with the word rapid. Now, you can think of probably many words, right? But I'm going to be nice on you. And I'm going to say, I'm going to tell you that the association is by way of synonym. So the pair is actually a synonym of the word rapid. But then I'm going to be even nicer, and I'm going to say the first letter of the word, of the pair, starts with the letter F. So please generate the word. Fast, right? Everybody, almost 95, 99%. Okay, NTU, 100% should get fast. You generated, I gave you a couple of hints, but all of you generated the words fast. To this group, I'm kinder. They expect everything to be given. Please don't take these experiments personally, okay? And I say, you guys don't need to generate. I will just give you rapid, and its letter is, and its pair is fast. Just remember that. In the same amount of time. So I go through 40 of these with you, each time showing you the stem, giving you a couple of hints, asking you to generate. You generate the correct one. And while you're doing all of that, I just tell them, hey, this is the actual pair. Just study and try to memorize it, because I'm going to test you on it. And after the experiment, I test you. What was the word associated with rapid and all the other 40 words? Who do you think does better? Group 1 or Group 2? Exactly. Right? But it's so intuitive that you got all the material, you didn't have to do anything, it was right. You could spend more time memorizing it. They spent time generating it, and then they were told, yeah, that's the correct one. So there's something about generating information that helps you. It's not just about reading and studying and memorizing. Again, it feels very intuitive that if I have the material in front of me, I can just read it. No, just give it to me. No. Something about generating. That's very key. So something about playing and tinkering, but there's something about generating itself that leads a better trace from a neural standpoint. Okay. But you might say, okay, this is generating the correct information. When I'm learning something new, I might generate most likely the wrong information because I don't know that thing. So let's do the same experiment. Group 1, Group 2. I'm going to give you a new word now, a new stem, and you've got to generate the response. This time, I'm not telling you any category or any hint. Okay? But you've got to just think of the word that goes with it. I think I use that word. Yeah. The word for you is dog. Go. Cat. Leash. Students, come on. Sorry? Puppy. Home. Bone. Thanks. Yeah, okay. Bone. What else? Pet. Yeah, pet. Yeah. Pluto. Okay, very good. Very creative answers, right? But they're all wrong. Because the word that I'm thinking of, and my word matters because I'm the teacher, I have the correct information, The word is mammal. So now remember, the association for dog is mammal. Thank you. And I come to you and say, don't bother. I will just tell you it's dog and mammal. Remember that? Same time. Okay? I do 40 of these here, 40 of these here. Give you a test after. Who remembers better? You guys all got all the notes, enough time to memorize? Well, these guys are still doing better. So it doesn't matter even if you generate the wrong information. That is still better than not generating. Not just not generating while they still have the correct information. Think about that. Think about that, how you think about your own learning. How intuitive it is to access information very quickly. The correct information, and try to study and memorize or learn it. But what the studies actually show how the mind works is that if you can try to build a habit of generating, even if it's the correct information, correct answer, correct misconceptions, wrong explanations for phenomena, wrong way of writing, wrong way of analysis, but it's your way of doing it first, and then get the correct feedback, like, sorry, it was not pet, it was mammal, right? That's far better than if I were to give you the correct explanations from the get-go and say, you guys are smart, study, evaluate, go for it. Okay? Very clear in the science, very robust. So there's something about generating even if it's the wrong thing. And if you think just conceptually, it makes sense, right? When I'm trying to remember something, I need a path to retrieve it. It's like a network. People who've learned it, just only the correct information, they have, let's put it very simply, one path is the correct path to that information. They have to remember dog, okay, mammal, one path. You guys, when I try to ask you the question about what's the association with dog, you'd say, oh, it was a pet? No, it was a mammal. You have two paths at least, depending on how many guesses you made. Because each wrong path leads you to the correct path. This is not philosophical, it's just how the networks work. The more paths you had to retrieval for the same information, the better the chance you're able to retrieve it. As simple as that. Okay? So the logic makes sense. The people who also studied tutoring. I'm sure you find yourself in maybe some of you tutor, and maybe some of you are tutees in different contexts, right? So people have studied tutoring situations because these are very commonplace situations. Maybe you are explaining to your colleague, your peer, you do tuition, or you take tuition. I don't know, right? But these situations are very common. And people have studied. If a tutor tries to explain the concept to the tutee as they are solving a problem, and the tutee is not stuck at anything, they're just going about solving the problem, the explanation by the tutor has no effect on learning. You know when there is an effect on learning? When the tutee is stuck, visibly stuck. Like, I can't do it, I can't proceed, I'm kind of stuck, I don't know what's going on now. I don't know what the next step is. If the same explanation were to come at the time where the tutee is stuck, or as they call it, at an impasse, the explanation has an effect on learning, right? So there's something about getting stuck. We think it's bad that we get stuck. We feel, I don't know, not good about ourselves as learners if we get stuck. But getting stuck and then getting the explanation is one of the most powerful ways of learning new things. So just to summarize all of it, right? To learn new things, you need to enter into a zone where there's failure. You will struggle. You will get stuck. There is something about playing and tinkering with ideas even before you learn what the correct thing is. There's something about generating information or knowledge, and we learn that even if it's the incorrect knowledge, it still helps you remember better. And then what this line of research suggests is there's something about getting stuck. Stuck is a good place to be, right? And if you put it all together, if all of these things are so important, then the logic of productive failure is simple. If learning from errors, learning from failure, learning from getting stuck is so intuitively compelling and scientifically supported, then why do we wait failure to happen? What if we could deliberately design for failure? What if you're trying, and this is all in the context of when you're learning something new. We're not talking about failure in exams and when the stakes are high. This is in the context of when you first come to understand something new, when you're learning something new. The idea is, can we design failure or getting stuck or struggle or getting you to generate the wrong ideas and information in that safe space where the stakes are low? Will it help you learn deeper so that when the stakes are high, the likelihood of failure is low? So I'm not talking about any kind of failure, just the early initial failure, right? And that's where productive failure comes in. And this is a two-phase design. So you would see on the right-hand side, there is instruction, there is telling, there is the teacher, the expert who will come in and tell you what the correct information is, just as I told you what the correct word was and so on, explanation was, and so on and so forth. But what is preceded by that is a carefully designed problem-solving activity that is challenging, intuitive, but is designed in a way that you can't solve it correctly. It's designed in a way that you can intuitively do many things, but none of them will lead to correct solutions. And in fact, you're told when you're doing that the objective is not even to get to the correct solution, because you won't be able to. You've not learned it. The objective is, can you generate as many ideas as you can? Can you be like group one, playing with this new toy without worrying about whether I figure out or not? That's phase one. And phase two is, once you've done that, then the teacher can do what he did to group two. Let me show you how to play with this toy. Okay? So it's a combination of group one and group two. And that's what leads to productive failure. So let me give you an example. Right? Suppose you're in high school. You were recently in high school, right? In secondary school until you came to the university. And this is actually data that comes from Singapore and other countries. We wanted to focus on the concept of standard deviation. It was a math classroom, right? And you all know what standard deviation is, I'm sure, right? Okay. Suppose I go to the class. So this is the new topic. They've not learned. They've not heard about this topic. They've not learned it. You go to the teacher goes to the classroom and says, hey, well, here are 3 football players. Here are the number of goals they've scored over a number of years in a league. Right? Option 1. It's a lesson on standard deviation. Can you calculate the standard deviation of each striker? What do you think kids would do? I don't know, right? It's the first time they're hearing about this. It's a new lesson. They've not learned about standard deviation. The teacher comes in, gives them a problem and says, can you calculate standard deviation? Well, that's precisely the thing I don't know as a student. So what am I going to do? Or you could ask it another way. Here's the same data. And I say, I know you don't know standard deviation. I don't care if you don't know about standard deviation yet. But what I do care is, can you look at this data and invent as many ways of deciding who's the most consistent striker? There's no mention of standard deviation or anything else. Like, just, here's a toy, play with it. Play as you like. So if secondary 2 and 3 students are given this, before they know the concept of standard deviation, they're just asked to invent as many ways of deciding who's the most consistent. What do you think they would do? Go on, please. Yeah. Any thoughts? What would they do?
Maybe the differences between the numbers, or like making the amount of difference.
Between what?
Between the numbers.
From year to year?
Yeah.
Okay, very good. What else might they do?
Compare it with the other players.
Compare it with the other players, okay. What else? I need some creative ideas. Can you be like group 1? You know, like 3 times more creative, so come on. Draw plot? Yeah, okay. So the guy did this. Draw plot and this. Okay, then what else? What's some of the early things you might do? Calculate the average. Yes, very good. Very intuitive. Anything else? Okay, well, I'm going to show you. This data probably comes from the time when you were in secondary schools as well, because this is more than 10 years old. So I would reckon you were in secondary school 10 years ago? Thereabouts, right? Okay, so this is from your peers, by the way, for most of you. Okay. So yes, they do take totals. Yeah, let's calculate the total number score, goal scored. Let's take the averages. Some of them know median and mode. They calculate median and mode. But we know that they're going to use that. We keep it the same. So that they try to solve the problem, but then they see they can't solve the problem using that. So they have to think of another method. They do tallying, they do box plots, and just to get a feel of the problem. You know, you're trying to figure out what the problem is. They do charts, as you said, up there. And you say, what's going on here? Oh, if it goes up and down a lot, it's more inconsistent. Okay, a good feel of the problem, but can you mathematize it? Can you be precise? Huh? They take maximum minus minimum. Again, very intuitive, or they may have learned the idea of a range. Again, we know they're going to use it, so we make everything the same, so they're stuck. Right? So it's a deliberate design where I invite you to use your knowledge, but because I know you'll use that knowledge, I make the problem not solvable by that knowledge. It's not evil, it's good for you. Right? Because then you have to pivot, you have to try something else, it doesn't work, it pivots on. All of this is very good activation of your cognitive system, so that when you get taught, as difficult or as effortful or a bit of struggle may be involved here, it is good for you, because when you're taught the correct concept, this is going to make a lot more sense later on, right? They take, I think your method was this year-on-year differences, right? You just take the differences, add them all up. The smaller the value, the more consistent. Some of them recognize that big values, you know, some of them are very large fluctuations, -9, +7, and so on and so forth. They tend to cancel out. So they say, let's ignore the signs. Let's make everything positive. Let's divide by the number of intervals. Let's get an average fluctuation. Again, very intuitive, non-technical mathematics going on. You won't find these solutions in any textbook, basically. But these are very intuitive solutions that solve the problem. Sometimes you get really creative solutions. Not that these were not creative, but here's a group of students who was asked to mathematize the graph, quantify it. I said, okay, imagine if I could hold the ends of each graph, line graph. If I could extend the graph into a rope. If I could calculate the length of that rope, the longer the rope, the more inconsistent. Right? And you might remember Pythagoras, right? A squared plus B squared equals C squared. They've divided that into 19 right-angled triangles, calculated the hypotenuse, and calculated the length of that, of each rope. And as I said in the morning, I've never bothered to check if the computation is correct. Because the math is not in the computation. The math is in the play of imagination, creativity. This is what's happening to group one before they learn the concept. If this whole exercise, if this whole design is designed really well, the problem and the activities are designed well, these are not about throwing any challenging activities at your students and you say, go figure them out. No, these are carefully designed activities. There's a design science behind it. But if they're designed well, this is the kind of play and exploration and generation of ideas and solutions that can go on before you learn the concept. And if after that, if a teacher comes in, consolidates and builds upon, like I said, that was the first phase. The second phase is the teacher coming in. Imagine if your faculty start doing this to you. Before my lecture tomorrow, which is on a new topic, I want you to solve this problem. You haven't learned the concept. Please do not even consult notes or Google or AI. I want you to just solve it based on what you know. Don't worry about getting it right. I don't even expect you to get it right. But I'm interested in the ideas that you produce, whether they're wrong, right or wrong. How do you think you'd react to it? Honestly. Would you go, no, your job is to just tell me. I pay for this university, please tell me. I'm pretty good at learning from telling. I got here by that game. Don't change that game now. Change it for the next batch, not for me. I'm teasing you. But the point is, how would you feel if that happens? Every now and then, say, before you learn something, this chap Manu Kapur says this is good for you. He's a bit evil, but he says he's good for you. He's backed by science. Okay, think about it. It's not trivial, right? It's because I'm suddenly throwing you into a zone where you've got to put in a lot more effort. But it's for your own sake. And it's hard to believe that because the other method is so intuitive. Okay? So it's not a trivial exercise. All right, so let's see if that works. So we do experiments. We compare productive failure with direct instruction. Direct instruction is the idea that I tell you, this is group 2. You don't know something, I'll show you how to do it, then you do it. Productive failure is like group 1 followed by group 2. I let you play and tinker, and then I show you exactly what to do. Right? So when we do these experiments, controlled experiments, classroom-based experiments, in schools, in labs, so we've done it in a number of places, and we look at how, so if you do pre and post examination of what people learn, we find that both methods are very good at developing high levels of basic knowledge. Like you get your stuff, you remember your formula, you remember your theorems, you remember your, and you can do some basic problems with it, no problem, right? You have high levels of fluency there. But the differences emerge in how deeply you understand them. Differences emerge in how you're able to transfer. If I change some parameters or context or make something novel, you're not thrown off. That means the knowledge that you have is a lot more flexible, a lot more adaptive. Okay, that's where the differences are. And like I said, this is conceptually to me kind of what productive failure looks like. I have the direct instruction path where I can go from the starting point and I can connect you straight to the correct answer. But in productive failure, the theory says, I will deliberately make you design the problem in a way that you go down these incorrect, suboptimal paths and then get you to converge in the correct one. And the evidence comparing them experimentally suggests the latter is better, even though it's a bit more effortful, maybe a lot more for some of you, but in the longer run, it's much better. But just a caveat, I'm not talking about any kind of failure. Please do not go and quote me and says, Manu says, failure is great. No, failure is not one thing, it is many. I'm talking about initial learning and failure, when failure is low stakes, but very powerful for learning. And that would reduce your long-term failure. Okay? And this is the failure that we need to intentionally, deliberately design for. Because what the findings suggest is the more paths you have, the more wrong things you generate, the deeper you learn. Okay? All right, this is just technical scientific aspect. So this is not just me. This program has been going on for about 20 years. I did the seminal work and some follow-up work. About 15 or 20% of the studies are actually mine now, which is great because in science you try to replicate and reproduce and extend basic findings. And so the work has been replicated immensely around the world in 4 different continents, 160 over experimental comparisons, and the average effect of productive failure. So imagine you learn through direct instruction with a good teacher for a year. And let's say I can put the learning gain on average to be 1 unit, indicated, right? If you switch to productive failure for that year, if you design it well, you can learn up to 3 times. So it's not an incremental effect, it's really a very large effect. Another way to put it, in terms of academic years, schools that switch to productive failure would have their kids appear 1 to 2 academic years ahead of other peers who don't use it or who use direct instruction. Not that we all want to get faster, but the point is you do learn deeper and you transfer much better, right? And although much of my work is in mathematics, the work has been extended to a number of domains. My interest is particularly in mathematics. And I want to stop with one last study, and because that's in the university context, so I wanted to share that with you. And this is a course. How many of you take mathematics? As in not the math course, but have you taken mathematics, first year mathematics at NTU? Oh, that few. Doesn't everybody have to take mathematics? Oh, okay, all right. ETH is different. Have you all heard of ETH? ETH in Switzerland, right? Home of Einstein and 30 other Nobel laureates. Might have. It's a small little university nobody knows about. Even I didn't know about when I got hired there. I said, what? So, but I found out it was a pretty good one. Okay, so here's a course. So every student, because we are a technical university, right? Every student, whether you're in engineering or computer science or architecture, every student at ETH has to do first year mathematics. And the hardest course in first year mathematics is the linear algebra course. You remember your numbers in rows and columns, nicely cozy in by 2 parentheses that mean something? Apparently it's a very important structure, underlying structure in a number of domains. Okay, and it's the hardest course. At ETH it's taught in the typical, so this is the large course, large lecture halls, 600, 700, 800 students. And it's taught in the typical sequence, lecture, tutorial, lecture, tutorial. I'm sure you're used to that, you're familiar with that, right? Large lectures, smaller tutorials. And so the math professor said, how do we use productive failure? I can't use productive failure all the time, I don't even know. So we formed a team, I got my PhD student to work on it. And we said, okay, this is a year-long course, hundreds of hours over the course of a year. So I said, we don't have to do productive failure, it's only for initial learning, only when you're learning the big ideas, big concepts. Give me 10 of those, 5 in the fall, 5 in the spring, right? And for these 5 topics, these 5 big ideas in each term, let us design productive failure, problem-solving phase before you teach that concept. And I said, you don't even have to worry about what they do, just teach as per normal. But just before you teach, we'll invite students to engage in these problem-solving activities. And we told students, look, you have not covered the concept in the lecture yet. Exactly the scenario I just gave you. But we explained to students saying, this is why we're doing it, it's good for you. So please volunteer. Right? So we didn't make it compulsory. We said, this is the logic, this is what the science says, this is why we're doing. We don't expect you to solve it correctly. But if you put in the effort, that lecture tomorrow or the day after is going to make a hell of a lot more sense. That was the contract. 70% of the students did it. Pretty decent, right? And the total investment over the course of these, so they did it 10 times, right? So in what is a hundreds of hours long course over the course of a year, the time the students spent doing those problem-solving activities prior to a lecture was only about 8 hours. So imagine one of your courses that lasts a year, lecture tutorial every week, and all we do is inject 8 hours surgically a few times over the course of the year. And here's the thing. This course has a historical passing rate at 55%. Because at ETH, it's easy to get in as long as you have a Matura or like an A-level. If you pass your A-levels, you're guaranteed admissions. Not like NTU, NUS, right? Entry is hard, staying in is a bit easier. Whereas at ETH, coming in is easy, but staying in is hard. Almost half of the first-year population goes away because the standards are high. We give you the opportunity, you meet the standards, if not, off you go. Different system, different logic, right? But that's the idea. Historically, the passing rate is about 55%. So here's the thing. If you take this year-long course, hundreds of hours, and you just inject productive failure surgically, total investment of student time on a volunteer basis is about 8 hours. Do you think we could change the 55% passing rate? How many of you think we could change it? Are you really sure? I guess the cue comes from the context of this lecture, right? Now comes the question. By how much should it change so that tomorrow you go back to your professors and say, give me those problem solving? I repeat, how much would you be impressed with These are passing rates, yeah? Toughest course on campus. As a student, I want to hear from you, how much do you think, if there's a change in the passing rate just by 8 hours, sporadically over the year, what would be an impressive increase in the passing rate for you to go back to your professor and say, can you please design these things before you teach me the concept? That's a fair question, right? So please put a number to it. 7%. You wanted to jump to 70, and then tomorrow you're going to go 8. Look, you have to look at the context. It's historically 55. These are the smartest kids in Switzerland. They're failing at a 45% rate. So seriously. 80, we take it 80, no problem. What else? What do you think? Commit to it right now. It'll just make things a bit more interesting. Don't worry, I'm not going to tell any professors. We'll just take notes, right? So, 63. Oh, like 8. Oh, well, okay, very interesting. A percentage point for each hour, something like that. 63, okay, good. So 63, tomorrow you're going to a professor and saying, please give me these exercises. Yes. Well done, I like you. Very good. Can we do more like this? More answers? 75. And tomorrow you are going to your professor and saying, we need this, right? Any more? You've got 80, 63, 75. Everybody's got their own metric, right? I want to hear it. What else? 90. Okay, tomorrow you're going and telling your professor. Okay, what else? Come on. Think of what is meaningful to you. 55 is just passing. 75 gives you an A, I think. I don't know. 90 is superb, outstanding maybe. Think of the students who are just failing. Can one more person commit? No? Now you're scared. Now you're just scared. Okay, so in the first year, we improved it by 10%. So we brought up the passing rate to 65. So you're definitely going and telling your professor tomorrow. And the second year, as we improved the design, we improved it another 10%. So I'm sorry, you are also going and telling your professor. The 80 and 90 kind of, okay, you're excused. But that's also a big ask. But think about it. Historically, if something has been 55%, and now the passing rate has moved 20 percentage points to 75, just by a simple surgical instruction. All that needed was a few students to be convinced, or the majority of the students to be convinced, when they were shared the science. They were made to understand why we're doing what we're doing, so that they could be invited to put in more effort for their own learning. That's all. And we found that, when we told them, please do not use anything else, they did not use anything else. Because it's ultimately for yourself. Right? So that's where, and this is the final part. There are 4 mechanisms that work here. Right? And this is why productive failure works. First is activation. We already covered. I use failure to activate your knowledge extensively, even if it doesn't work. Right? Because there's something about generating and activating knowledge. Right? Second, it makes you aware. Like once you've tried a number of ways and it doesn't work, you become aware that there's a gap. Right? Oh, I could do something, but I could not get to the correct answer. There's a gap. And psychologically, humans are built to not run away from the gap, but you want to close the gap, especially if you've invested in it. Right? You've invested time and effort in it, you want to close the gap. You want to know what the correct solution is. So your interest, your engagement, your motivation, even a little bit of frustration because you tried many things that didn't work, even a little bit of negative emotions, damn, I don't like this, I can't get to the correct answer. All of these are actually very good for your learning. You're used to thinking from an affective standpoint that anything that makes you feel good and happy and makes things easy, eases learning, when in fact it's quite the opposite. Things that make you struggle, things that may you even fail so that you enter the zone. In that zone you won't feel terribly good about everything. It'll be a little bit of stress, it'll be a little bit of anxiety, a little bit of doubt that maybe this is not for me, I'm not getting it. But that's precisely the zone where you need to tell yourself, I'm right in there. This is exactly where I need to be. Because if at this time, if an expert comes and assembles it, your activated knowledge with your awareness, with the right affective state, you're primed to then listen to the teacher or the expert assemble the knowledge for you. And that's why productive failure works.